Hello and welcome. My name is Alexander. This is joint work, and today I'm going to present aggregation and garbage collection for online optimization. Let's dive in. So we're looking at online problems, also called dynamic problems, or decompositions of static problems, offline problems, via rolling horizon or sliding window. So let's look at this animation up top here. We have some tasks. We need to schedule them. Time moves forward. Some tasks can't be changed. Some tasks can be changed. And we get new tasks over time. Okay. Well, the size of the instance grows every time new data arrives. We saw that, right? And new data arrives all the time. This will, of course, slow down processing after a long while, right? We will have millions of jobs, maybe, and this is going to really slow down processing. Some variables and data are realized, meaning that they will never change. Look at task 1A there. Now look at task 1B, right? Those are completely in that gray zone, which means that they can't change. They are in the past. The past can change, of course. The past has already happened. So there's no uncertainty there, right? And removing all these realized data and variables are not that straightforward in the problem-independent setting, right? It's not that straightforward, unfortunately. So let's look at that, that little graph there to the right. This is the motivation behind this, right? So in another paper, we saw that when we modeled these online problems, if we didn't have any garbage collection at all, the compilation time skyrocketed after a while. But if we had a really simple garbage collection mechanism that was specific to that problem, then we got really good improvement there. So we want to do this problem independently. What are the steps? The steps is number one, identify realized data and variables based on modeler's input in constraint analysis, right? So this is the problem, this is the little problem specific thing that needs to be there, but everything else is basically problem independent. Step two, aggregate, meaning we summarize the effect of realized data and variables. We do this via model reformulation. Step three, garbage collect. We filter out all data that's left over and not used anymore after this aggregation. And as I mentioned, this is a problem-independent framework. To conclude, this is an important step forward in modeling online problems. What did we do? Well, we are now able to systematically infer realized data, variables, and objects. Modeler provides basic information, but that's all. Now, we also look at how to aggregate common constraints. And a very interesting future work is to create a big library of all these aggregation of constraints. And lastly, we also looked at how to perform problem-independent garbage collection. Okay, let's move on to the technical talk. Let's look at this online problem once again. This example here, right? So we have these two tasks. We have a current time. And then we allocate some time that we want to solve this problem. This now line here is very, very important because anything before that will refer to the past when we're done solving. So we call that the forbid zone. We're forbidden. We can't put anything there, right? So when we schedule these 1A and 2B, we need to put them over there. Okay. Time moves forward. The now line moves forward, everything moves forward, of course, and we get the new tasks that we saw before, right? And we don't know this beforehand. This just arrives, and we're like, okay, now we need to handle these tasks. Now, there's another interesting comment, and a concept here. This is what we call the commit zone. What does that mean? Well, any decision that's in this zone is now also committed. We can't change that decision. Right? The decision that 1A started at that time, that is committed, right? We can't change that because that's changing the past. But 2B, that's not committed, right? We can move that forward and we can put them there, right? So that's basically the basics of an online problem, right? Let's go back to the motivation. So previously when we modeled or tried to solve these online problems, there were only problem-specific methods, right? If you want to solve this kind of problem, you had to do it this way. If you wanted to solve another kind of problem, you had to do it another way. And if you changed your problem a little bit, well, tough luck, because you had to change a lot in your implementation, in your algorithms, right? But why not have a high-level modeling language. We had a paper at AAAI 20 where we introduced such a framework. We introduced a problem-independent framework to model these kind of online dynamic problems, right? And this was a really big step forward, but we realized one problem. The size of the instance grows every time new data arrives, as we saw, and processing slows down. But as we saw, some variables and data are realized, meaning that they will never change. Another question is, can we remove them? And how do we remove them? And how do we know what we can remove? What do we need to keep? What can we completely remove? And what can we like maybe summarize to just one little thing instead of having 100 of jobs, right? Maybe we can put, instead of hundreds of jobs, we can just put that in some kind of like combined information about all those jobs, right? What kind of things can we do? Because removing them automatically in a problem-independent way is not that straightforward, but we still want to do it, of course, because we want to have a really good and fast solving method. Okay, so there's one important concept that we learned here. That's modeling with named objects. So in Minisync, which is the language that we used when we ran the experiment, so we used this, there's something called enums, right? So if you see here, we have the vehicles, number of vehicles, number of customers, right? This is a standard way of modeling. And then we want to model, okay, what vehicle visits that customer, right? So we have an array of the set, index set, 1 to customers. Each of those indices is a variable of the domain 1 to vehicles, right? So now we can represent each vehicle and each customer like this. And then the problem here is when we have this online situation, we move forward in time and we want to do garbage collection. Okay, now vehicle 3 or vehicle 1 doesn't mean vehicle 1 that what vehicle 1 meant previously, right? So what vehicle 1 refers to will change, right? Because we always will have this 1 to vehicles. And one way to circumvent this is to like create some new index set with a lot of mappings in between, but this can be done for free in Minisync. We just introduce an enum here, vehicles, right? And this will of course have cardinality m. But the objects here are named, right? V2, V5, V22. We can have whatever kind of names here we want. The customers, C1, C53, C123, right? So we can see here, maybe some of the customers here are garbage collected. They aren't needed anymore, right? And this fully support that. And at each iteration, this will be a contiguous index set. Okay, so this is an array of customers, and it's still the same thing as up here, visits. Which vehicle visits that customer? Okay, and another really nice thing we can do here is that we can create object sets, named object sets, or we can also call them enums, from other enums, right? So we can create a function s here. S of vehicle, which is the start nodes, start depot, plus the end depots, plus the nodes of that customer, right? And now that's all the nodes. Up here, in order to do that, we had to do this weird thing. And now the mappings aren't that obvious anymore, right? Down here, we can get the mappings for free by design. We just use the E, S, and N functions, or the inverse of them, right? Okay, let's look at the quick dynamic VRP example before we dive into some details. As we saw, we have an object set of vehicles, we have an enum of customers, and we have the nodes. Then we have the distance, the travel distance from one node to another. And this is created from XY coordinates of vehicles and customers, right? We have some decision variables here. We have what vehicle visits that node. What's the arrival time at that node, right? When does the vehicle arrive? What's the next node given a node? And then we can do this circuit, right? So, and this is the idea behind this node here. We have the start depot and the end depot. Even though that's maybe the same depot, we can have this grand circuit that loops through all the customers and all the starts and end depots. And then we get this big, nice circuit. And we get this really strong constraint, circuit constraint, right? But the problem is, how does aggregation and garbage collection work now when we have this circuit constraint, right? And that's a tricky question. Let's first look at realizations. What are realizations? What's the definition of realizations? Okay, so we'll look at variables and data, and then we'll look at objects. Let's start with variables and data. So the first definition is it has happened. Okay, it has happened, right? If it has happened, then it's realized, right? If the arrival at n, if that time is earlier than now, and remember now meant the solution's reference of the current time, right? So that's essentially in the past when we get the solution. All right, so the arrival has already happened. That means it's realized, right? Because we can't change the past. Or another definition is that it will never happen, right? The travel time between two nodes that will never be used, for instance, right? If one of the nodes, we already know the successor, and the other node, we already know the predecessor. We will never travel between these two nodes because we know the predecessor and successor, so we can throw away that travel distance. Now, here is the little problem-specific part that is left that we couldn't get rid of. This needs to be given by the modeler. This is problem-specific, right? Because some of these details are really nuanced and you require expert knowledge of what these parameters represent in the real world, right? So it becomes quite tricky here. But if you're a modeler, it should be quite easy to think of this and realize, yeah, this is the criteria for this being realized, and this is the criteria for that being realized. Yeah, as I said, essentially the only problem-specific part. Objects, okay. We saw the enums. What about objects, right? The object n is realized if all variables and data indexed with n is realized. Okay, and this also includes indirect usage via constructed object sets, right? So it's both n as a node and n as a customer and n as a vehicle and whatever, in whatever way that's possible, right? So we have that mapping between. And we will always reason on objects from now on because it's much more easy. Okay, aggregation. What happens? Well, we summarize the effect that realized data and variables and objects has in the future, right? There's basically 3 steps to do this. Find what can be aggregated for each constraint, redefine the constraint to allow aggregation, and then step 3, introduce and define the aggregated value, right? And we reformulate the model to automatically calculate this during compilations, right? So this will be built into the model, to the minisig model, and whenever we compile, things will be aggregated automatically. Let's look at an example here. Let's say we have a sum. 0 is equal to this sum. Okay, we loop or we sum over an index I, and we have ci times xi. Okay, we don't really need to know what this represents. We know that ci is a constant, xi is a variable, and I is some index. Right? We can split this up now because as we saw before, I is an object, and I can be then split up to a realized set. This is the orange sum there, and then the black sum is the non-realized one. Okay, let's now replace that orange one with an aggregation. And let's go to the next iteration. What do we have now? Okay, yeah, now we don't have I is non-realized anymore. We just have I, right? Because there may be new items going on here, maybe new objects going on there. So we need to split that up. We need to split that up again. So now we have that purple version here of the realized sum, and we have this non-realized one. Let's replace that with an aggregation again. Okay, so now we see the pattern here. We have aggregation prime, then we have that non-realized sum. So in general, we can actually look at the sum like this. We rewrite the sum from up here to down there to just have an aggregated value plus the non-realized sum. And we define the aggregated value to be the sum of the realized values plus any previous aggregated value that we possibly had, right? In this purple one, egg prime, the orange egg would be the previous one. Okay, let's step to circuit aggregation. Much harder to look at the global constraints, but we figured this one out. Okay, let's see here. We have A, the successor of A is B, the successor of B is C. Now we see these dotted lines, they're not realized yet, but these fully drawn lines and these double rounded nodes, they are realized, right? So if the successor of C is realized to be D, and the successor of D is realized to be E, and the successor of E is realized to be F, right? Then we can just do a short circuit directly from C to F. As we can see here in the second picture here on the right. We go directly from C to F and throw away E and T, right? We can't throw away C because something needs to point to it. And so we can see, as an example here, maybe A now points to C instead, right? And this is the aggregation in the circuit constraint. And in the travel distance constraint, that is, the similar aggregation will go on there. And if we can also throw away E and T there, then that will take into consideration to whether the sum is calculated there, right? So we all throw away these kind of aggregate away these objects. Okay, garbage collection, right? This is the last step. What do all constraints agree is garbage, right? We saw that some things was not needed anymore. It's replaced by aggregated value, right? That which is never used anymore and replaced with aggregations everywhere, right? We can simply scan the model and see, or scan the instance rather, and see, okay, what is not used anymore, right? Simply remove that when generating the instance, right? It will still be in memory during that compilation, but we removed this once, and now we'll remember that in all future compilation steps, right? It will completely gone in the next solving session and future solving sessions. Let's quickly look at some experimental results. So what do we see here? Well, we see a job shop scheduling problem with one very long tasks. With one very long task, right? So one of the tasks are like a few time units, and the one task is huge, takes a bunch of time units. Okay, this really shows the really good things with this named object sets. Right, so if we have no garbage collection, we can see we can handle up to 44 jobs, 11 instances, and then we die, right? Simple garbage collection, this is what we did in our previous paper. We just write some very simple thing, problem specific, and we just remove the first occurring jobs. But because the first job is really long, that will halt everything and will still die, right? But our garbage collection is really fast, and you can see it's still, after like hundreds and hundreds of jobs, it's still really fast. And we also have results of the vehicle routing problem in the paper, so you can see that if you want to. Okay, now, to conclude, as I said before, this is a really important step forward in modeling these online and dynamic problems, because we don't want to have these problem-specific algorithms anymore. We want to have a high-level modeling language. We want to have a CP, we want to have MIP, we want to have all these powerful high-level things. We don't want to deal with small, low-level algorithms when we're dealing with these complex problems, when we can deal with it at a modeling view, right? So it's a really important step forward. And what do? Well, we are now able to systematically infer realized data, variables, and objects. The modeler provides some basic information, which is the little problem-specific step that is left. But essentially, this should be quite straightforward if you know what kind of problem you're modeling. We're also able to look at and aggregate common constraints, common global constraints, common combination constraints, right? And obvious future work here is to create some kind of aggregation library. And finally, how to perform problem-independent garbage collection in these high-level online models. Okay, that's the end. Thank you very much for listening. If you have any questions, don't hesitate to ask, and thank you.